Okay, before we get into the reactions of carboxylic acids, I want to go back and talk a little bit about the factors that affect carboxylic acid acidity and maybe review some of the other ways that oxygen molecules can be acids. So one of the things that we know is on our periodic table of CNOF that basically the basicity will increase as we go from right to left on the periodic table. But there are a number of different types of O- that we can take a look at. So if we go back and talk a little bit about alcohols, let's just take methanol as an example. So we'll have our CH3OH. And what we know is we know that the acidity equilibrium is going to have the alcohol give up a proton to form the alkoxide and the proton. Now, the way that we typically look at strength of acid is that we look at this and we say, well, anything that pushes the equilibrium to the right will increase the acidity of this system because that will allow us to produce more H+. So again, our general rule is, how do you push equilibrium to the right? The way you push it is you make the products more stable. Okay, and in this case, what I'd like to do is I don't want to push electron density into the O-. What I'd like to do is I'd like to withdraw electron density out of the O-, which would make the alkoxide more stable. So one of the things that you could think about is, well, how do we do that? And one of the ways to do that is to replace, for instance, that hydrogen with maybe something like a halogen, like a fluorine. So if you looked at the acidity of trifluoromethane, one of the things that you'll find is that as we form the trifluoromethyl alkoxide, that because the fluorines are going to be able to withdraw electron density from the O-, that's going to make that more stable, which is going to push the equilibrium so that this would be a stronger acid than something like CH3OH. Now, the problem here is that for alkoxides, using these inductive effects, right, because this is really using induction as we talked about with electrophilic aromatic substitution. Remember, induction is to withdraw electrons using electronegativity effects. That we can only go so far. So alkoxides aren't going to be as strong of acid or strong of bases or strong as strong of acids. Alcohols won't be as something else. So the next thing we'll talk about is carboxylic acids then. So if I have something like a carboxylic acid and I write its equilibrium, what am I going to end up with? Well, I'm going to end up with the carboxylate, right? And the carboxylate is going to be stable by resonance, right? Because I can take this pair of electrons, move here, move that pair of electrons, so I can draw two resonance structures for this. So that's going to make the carboxylate more stable than, let's say, more stable than an alcohol. And so this is going to be a stronger acid. So when we look at the carboxylic acids, they're going to be stronger acids than alcohols are. And again, my goal here is to look at just the O minuses to begin with. Now, the other thing that we've seen in the past is we've seen, well, what happens when you attach the OH to the benzene ring? And when you attach the OH to the benzene ring, remember that's called a phenol. And when I deprotonate that, or when I form its conjugate base, I'm going to form a phenoxide. Now, a phenoxide can be stabilized by resonance of the benzene ring. So we could take this pair of electrons, move here, and then move that pair of electrons to form our carbanion. If this looks familiar, this is exactly what we did in nucleophilic aromatic substitution. And basically, in terms of resonance structures, there would be two more. You know, if you're overly ambitious, you could go ahead and draw those out. But the idea here is that a phenoxide then is going to be more stable than a regular alkoxide. But because each one of these resonance structures breaks up the aromatic ring, so in other words, if I'm looking at this ring system, yes, it forms a resonance structure, but that's breaking up the aromatic ring. It's not going to be as stable as the carboxylate. So when we look at oxygen species, what we find is the following. We find that a carboxylic acid is stronger, greater than a phenol, which is going to be greater than the run-of-the-mill alcohol. Okay, so this is acidity, or well, let's just call it acid strength. So of the oxygen species, the alcohol is weakest, and the carboxylic acid is the strongest. Okay, so as we look at this, that's what we want to think about in terms of carboxylic acid strength. Now, what can I do to make carboxylic acid stronger? Well, I'm going to need a new slide here. Take a couple of them. So let's talk about using inductive effects in this like we just did with the alcohol. So in other words, if you want to make a stronger acid than this acid, which is called acetic acid, we've used this in lab. If I want to make this stronger, what I should do is I should attach electron withdrawing groups like halogens to that acid. So that way what happens is when I form my equilibrium, the fluorines are able to withdraw the electron density from the carboxylate and therefore stabilize it by induction, so that again we push that equilibrium to the right and make, in this case this is called trifluoroacetic acid. And it is a much stronger acid than just acetic acid because of the effect of the three fluorines. Acetic acid is basically the main component of vinegar. You get vinegar on your skin, no problem. It's not going to It's not going to burn it. It's not going to cause, basically a chemical burn. Trifluoroacetic acid, and I know this from personal experience, if you get trifluoroacetic acid on your skin, it'll leave a mark. And then your biggest problem is getting it infected. But had that happen once with an NMR solvent. I dropped the vial of it, and it broke open and splashed on my legs. I think I still have the scars from that. So trifluoroacetic acid is a much, much stronger. As a matter of fact, trifluoroacetic acid is what they use to remove moles. Put a drop of that on there, and it basically will burn that off chemically. Now, this effect gets weaker as the fluorines get farther away. So if you put the fluorines, for instance, on a methyl group, but then have a CH2 group in between the carboxylic acid, that's going to be weaker than trifluoroacetic acid. But it will still be stronger than regular acetic acid. So the idea here is that as we move those electron withdrawing groups farther from the carboxylic acid and farther from the carboxylate as its conjugate base, the acid will get weaker. Now, what about benzene rings? Well, if you have a benzene ring, then you can do the same thing. You can basically think about, okay, my benzene ring is going to dissociate to form the benzoate, which is going to be the carboxylate of benzoic acid. And if I want to make the benzoic acid stronger, what I need to do is I again need to pull that electron density away from the carboxylate, from the basically O-. What kind of group am I going to add to the benzene ring to withdraw electron density from it and make it, in essence, more stable? What kind of group should I add? And if you said an electron withdrawing group, you would be correct. So if we had a series of benzoic acids, and again, what I'm doing is I'm making the conjugate base more stable. That's pushing the equilibrium to the right and making the benzoic acid stronger. So if you had, for instance, a benzoic acid with, let's say, a nitro group and let's put a fluorine on there versus benzoic acid versus, now let's do the opposite. And let's add a methoxy group. If we were to rank these, I actually rank them in order of acidity. So in terms of acidity, the nitro being the most electron withdrawing group in this series would be a stronger acid than the fluoro, which would be stronger than an H. Remember, H was our baseline, which would be stronger than an actual electron donating group, because the electron donating group is going to push electron density into the ring. And if I come over here, the electron donating group is going to push electron density into the ring, pushing it into the C double bond O-. And the problem there is that now I'm trying to push electron density into the negative charge as opposed to remove it, and that's going to make it less stable. So that's how we would look at the acidity of carboxylic acids and substituted benzoic acids. Okay, so that's a little bit about to kind of get us to get caught up here in terms of the acidity of carboxylic acids and how they rank in other oxygen species. Now, the practical aspects of this, just to finish this up, is that, remember, if you're trying to take an alcohol and convert it to an alkoxide, what kinds of bases do you use? And I'm talking bases here, not sodium metal, not potassium metal, which would work perfectly fine, but that's a redox reaction. So if you said you could use a C-, an H-, or an N-, you are correct. Why? Because we've got CNOF, our H is over here. Basically an H- and a C- are roughly equivalent to each other. And then the N-, so what I need is, I need a base that is stronger than oxygen. So N-, O-, or sorry, N-, C-, or H-. So I need to use a stronger base. Okay. And just to go back here, let me make sure that I got this right. Yes, as we go from right to left, the basicity does increase for the across that periodic table. So looking at that, then, it takes a stronger base to make an alkoxide. Well, for a phenol to convert it into an aphenoxide, what kinds of bases do I need to use here? Well, I can use a C-, an H-, and an N-, but because this is a stronger acid than the alcohol, I could also get away with sodium hydroxide. That would work. So that just shows that the phenol is a stronger acid. Okay. What about a carboxylic acid? Carboxylic acid I could use to form the carboxylate. I can use, again, a C-, an H-, an N-, and those would be overkill. I can still use a hydroxide, but now I could use something like bicarbonate. So I could use bicarbonate to do that reaction. So again, showing these are all getting weaker in terms of basicity as we move across. As we move this way, these are getting to be weaker bases. And the fact that my carboxylic acid is a stronger acid means that I can go ahead and use a weaker base. Okay, so that's where it practically comes into effect, and I'll show you with carboxylic acids what that means in our Fischer esterification. So let's talk about Fischer esterification and other reactions to make esters from carboxylic acids. So in lab, we took the acid, carboxylic acid, we reacted it with an alcohol. This is an equilibrium reaction. It requires H+ as the catalyst, and we ended up forming our ester and water to balance the equation out. We'll go over the mechanism of this in a moment, but let's just talk about the practical aspects of it. The big issue with this is the fact that it is an equilibrium reaction. So therefore, if I want to make an ester in the highest possible yield, I need to somehow push the equilibrium. Now, we've talked about pushing equilibrium mostly in terms of making the products more stable, But this is one of the situations where we're going to go back to our friend Le Chatelier and just go ahead and use Le Chatelier's principle to push the equilibrium to the right. That means that if I want if I want my highest yield of ester, what I should use is an excess of one of the reagents. I will typically use an excess of the carboxylic acid, and I'll talk about that in a moment. You could use an excess of alcohol, but it's going to create a bit of a problem. Or the other thing you can do is you can remove the water as it's produced. And there are actually apparatuses that you can use that as you reflux the alcohol, carboxylic acid, and we use sulfuric acid as our catalyst, as you reflux that, you can actually remove the water as it's produced and therefore push the equilibrium to the right. Typically, we will use an excess of carboxylic acid. So if we use an excess of carboxylic acid, that will push the equilibrium by Le Chatelier's, using a Le Chatelier principle. Now, why do we use an excess of the carboxylic acid? Because if you can imagine in our round bottom, at the end of the reaction, we're going to have ester, of course, hopefully. We're going to have some unreacted carboxylic acid. We'll probably have a trace of unreacted alcohol, and we're going to have water, and we're going to have our acid catalyst. So that's going to be in our mixture at the end of the reflux period, and we did this in lab. Well, I can remove the water basically by drawing on, I want the ester. I can remove the acid by basically adding water and extracting. So how do I remove the product that I want? And the product that the reactant that I want to remove is I want to remove the acid. So what do? I actually treat this with sodium bicarbonate solution, which means that it's dissolved in water. And what happens? The sodium bicarbonate reacts with the H+ catalyst. It also reacts with the excess carboxylic acid and converts it to a carboxylate. Now in my round bottom, I end up with two layers. The top layer is the ester and probably a trace amount of alcohol. And in the bottom layer, I end up with water. I end up with neutralized H+, and I also end up with my carboxylate. Why? Because remember, it's ionic and will dissolve into the water. So this is a really easy way to do an extraction so that if I use excess carboxylic acid, I can remove it at the end of the reflux. And if we would have done that in lab, or if we are doing that in lab, then we would basically extract this with sodium bicarbonate. The biggest problem is that, remember, with H+ reacting with HCO3 minus, that you end up forming H2CO3, which is called carbonic acid. The problem with carbonic acid is that it dissociates to form CO2 and water. And so when you add the sodium bicarbonate, you have to be really careful that you don't immediately cap the separatory funnel and start shaking because your product sprays all over the place, because you've now generated basically carbon dioxide. Carbonic acid is in your favorite, is in whatever your favorite carbonated beverage is. Okay, so that's a practical lab aspect of it that fits into what we did in lab. Now, the biggest problem with doing Fischer esterification is this equilibrium. You got to reflux it for a couple hours, which is what we did in lab. Are there better ways to do this reaction? Are there better methods? And the answer is yes, there are better methods. And we'll talk about this mechanism here in a moment. But the better methods would be let's take our carboxylic acid and let's convert it to an acid chloride, and then react it with our alcohol. Now in this case, there's no equilibrium. I'll talk about this in the mechanism in a moment. I can make my ester and HCl in 100% reaction. There's no equilibrium here. So the better method would be to convert the alcohol to a acid chloride, or sorry, a carboxylic acid to an acid chloride, and then react it in 100% reaction with the alcohol. How do you convert an alcohol to a carboxylic acid? How do you convert a carboxylic acid to a carboxylic acid chloride? You could use SOCl2, you could use PCl3 or PCl5. That's the way you do that. So that's a better method overall. Yes, it's 2 steps, but it overcomes the equilibrium issue that we have with Fischer esterification. There's some technical issues with this, like you have to avoid water and other things. But if you have the right conditions, you can do this a lot easier. The other thing to do would be, once you've made your carboxylic acid chloride, you could also react it simply with the alkoxide. And that's going to be a little bit more difficult, but if you could do that, the O- will come in and directly attack the carbonyl. And then, as we've always said, when you add nucleophiles to carbonyls, the pair of electrons is going to want to come back down and reform the carbonyl. It can only do that if there's a leaving group. What's a better leaving group, chloride or OR? Let's take a minute to review. Leaving group ability is based on one thing. And what is that? It's based on basicity inversely. Which is a better leaving group? The weaker base. Which is the weaker base? Chloride or alkoxide? Definitely chloride. So we lose the Cl- and we end up easily forming the ester. Technical difficulties in forming the alkoxide. You got to keep it away from water and some other things, so that might not be really great. So let's look at a third one. The third one would be to say, okay, we know how to make a carboxylate salt. Can I do an SN2 reaction using something like a primary alkyl halide? It works great with a methyl alkyl halide, so in other words CH3Cl. I can just simply do an SN2 reaction, and I can make, in the case of a methyl, I can go ahead and methylate that carboxylate. So that would be another high yield method to make in this case, a methyl ester. You're going to have limitations as to how big that primary alkyl halide can be. So these are better methods to make esters using, in some cases, SN2 reactions. Now, let's talk a little bit about the mechanism here. Now, the mechanism for this reaction is going to be relatively straightforward. It's going to be complicated with a lot of steps, but so the first step is to protonate the carbonyl group. And I'll talk about why you don't protonate the OH group of the carboxylic acid in another slide. So first thing is I'm going to protonate the carbonyl group. We did that to form hydrates and to form acetals and hemiacetals and ketals and hemiketals. So same first step. Shouldn't be anything exciting because that's what we've done in the past. Then the next thing is our alcohol will come in as a nucleophile and we'll add to the carbon. And these are all equilibrium steps in Fischer esterification. I add the entire alcohol. So that now I form the oxonium ion, and then I'm going to lose my H plus to form that species. Now this is the first time we've drawn that species because yes, we've had an OR group. In the past, we've had an OR group and we've had an OH group, but now we've got two OHs and two ORs, or just one OR, two OHs and one OR. So now the next step is that I'm going to react one of those OH groups with the acid that I just lost. Again, if I protonate the OR group, I go backwards. So let's take the top one. It could be either one, actually. So when I protonate that oxygen, that OH group, I'm going to form my oxonium ion. And I'm going to form that species. Now, there's a couple of different mechanisms that textbooks use for this reaction, and I would accept either one, so I'm going to show you both of them. The more explicit way of doing this is to say, okay, now I'm going to lose the water, right? So I'm going to lose water. That's where the water product comes from in Fischer esterification. I'm going to end up with that carbocation. And then this is going to be stabilized by this resonance structure. To form that, and if you're looking at that, that is a protonated carbonyl. So then we just simply regenerate our catalyst by losing H plus and forming the final ester product. So this is the entire mechanism for Fischer esterification. In my lab, I'm going to ask you to write the mechanism. Do not write the mechanism with the R groups. You're going to be cautioned against that. So you're going to write it with the actual alcohol and carboxylic acid that you figure out what your ester was made from. Don't write it with R groups. And for God's sakes, do not copy the R group mechanism that is in my handout. I just went through some lab reports from last year, and I think TAs were very forgiving. They're not going to be this forgiving next year when you just this year when you just copy and paste my mechanism. You're going to have to write it on your own. So here is the mechanism for Fischer esterification. Now, the alternative that some books do, and I'm just going to simply rewrite the oxonium ion structure here. I'm going to put the bond in explicitly. Some books will just do this. They'll take this pair of electrons, move it here, and then have the OH group kicked off. And when that happens, you end up with the carbonyl group. You end up with the ester minus with H2O being formed. I don't honestly care which mechanism you use. This is 2 steps versus this step is 2 steps. versus 3 steps, it really doesn't matter, as long as you understand the fact that you are remaking this carbonyl and forming the ester and losing the water either in 1 step or in 2. Okay. So that is the Fischer esterification mechanism. Now, you can do Fischer esterification to form cyclic esters, which we call lactones. So just to make you aware of this, because the textbook talks about this, if you took, for instance, something like this, where you had an OH group on one end of the molecule and a carboxylic acid group on the other. So you have an OH group and a carboxylic acid group. You can treat that with H plus H2O. Or sorry, just H plus, and form a cyclic ester, which is what is called, that's what a lactone is a cyclic ester. Now when you're writing the ring, I like to number out the carbons so I know how big my ring is going to be. So I've got carbon 1, carbon 2, carbon 3, 4, 5, and then the oxygen would make the 6. So that OH group is going to basically wrap around and attack the carbonyl, so that I'm going to end up with a 6-membered ring. One of those is the oxygen, which I call number 6. Then we'll go 5, 4, 3, 2, and 1. Carbon number 1 I should put there, because carbon number 1 is going to be the carbonyl, and then CH2 for carbon 2, CH2 for carbon 3, CH2 for carbon 4, and CH2 for carbon 5. So in this case, we would make a 6-membered ring lactone. So you can make lactones by using what is called an intramolecular Fischer esterification. Okay, so that's our intramolecular Fischer esterification. Okay, so that is the mechanism and how we can convert carboxylic acids into esters, both open-chained esters as well as lactones, and the mechanism for doing so. And we're going to find that these mechanisms really are very similar, except we're going to have different groups that we're adding, and we're going to have different leaving groups. So that's Fischer esterification, the mechanism. There are other ways to make carboxylic acids, and mostly what are called methyl esters. So one is to use diazomethane. So diazomethane utilizes the fact that you have a nitrogen group that will be the leaving group. So in this case, what I'm going to do is I'm going to react my carboxylic acid with diazomethane. And diazomethane looks like this. We saw this with basically with using azide. It's something very similar before. The nitrogen has a plus charge. This oxygen on the end has a negative charge. So what's going to happen in this mechanism is the following. There is a resonance structure that I can draw for this. Let me just draw that. Take this pair of electrons, move it here, and then move this pair of electrons out to the carbon. So the resonance structure for diazomethane looks like this. The nitrogen still has a positive charge, but then it puts a triple bond to the nitrogen. Now, if in this resonance structure there's a C minus, that can go ahead and deprotonate. That can deprotonate the carboxylic acid. So that what we end up doing then is forming a carboxylate, and now having CH3 and that diazonium salt. Okay, or this sorry, the protonated diazomethane molecule. Now what will happen is the following: that O- is going to do an SN2 reaction. So this minus charge comes in, reacts with the methyl, and just like we saw before, this is a great leaving group as an N2. Pair of electrons will go to the nitrogen, so that what I'll end up doing is I'll end up forming the methyl ester by adding the methyl group to the O- and forming nitrogen gas. So this group will be a great leaving group and will end up methylating the carboxylic acid. So this is really kind of an old school method. You have to generate the diazomethane. There's actually specialized glassware for that if you want to go ahead and make a methyl ester using the diazomethane approach. That's relatively straightforward, and again, it utilizes the fact that this group right here, this group is a really good leaving group. So that's diazomethane to form a methyl ester. And I'll talk a little bit about methyl esters when the R group over here is a long chain. Those are called fatty acid methyl esters, or FAMEs, and I'll talk about that in a upcoming slide and reaction. So diazomethane is a really old school method of forming that. Now, we talked about in the previous slide taking a carboxylic acid, deprotonating it, and then reacting it with methyl chloride in another SN2 reaction. We could use, again, we'll just use bicarbonate for this reaction. We could use hydroxide or any of our other bases. Basically, that's a similar reaction to what we saw, only the leaving group is different, so that we could form our methylated ester, or our methyl ester, by using that method as well. So we saw that in the last few slides. Okay, the next reaction is one that I believe I talked about before, but we'll go ahead and review this. That's converting carboxylic acids into amides by reacting them with amines. So if you remember correctly, if you take a carboxylic acid and you react it with an amine, we'll take a primary amine here. What happens is you get, first of all, an acid-base reaction where the nitrogen deprotonates the carboxylic acid, and you end up forming the ammonium carboxylate. You do not add the amine to the carbonyl, right? This is an acid-base reaction. Now, if you want to heat this, and I think in the previous lectures I talked about when my first graduate student, when we were trying to do this reaction, we ultimately had to resort to a Bunsen burner and heating the virtual crap out of it. You'll end up condensing, meaning lose water, and you can end up forming then the amide, and you end up basically producing water. And that's, whenever you produce water as a reaction, just in terms of terminology, that's called a condensation reaction. So you can do this reaction fairly straightforwardly. Again, it just requires a tremendous amount of heat. hot plates don't necessarily cut it. So that's how we can form amides. But remember, this is the critical first step. So don't get trapped into adding the amine to the carboxylic acid, carbonyl. You do an acid-base reaction, then you have to heat it in order to form the amide. So we reviewed that one. Now let's talk a little bit about the reduction of carboxylic acids. Before I do that, I want to talk about the whole carboxylic acid to primary alcohol scheme. So if we start with a primary alcohol, we know that we can oxidize that to an aldehyde. And once I figure out how to do this, how to actually make the videotape stop and have you type in the reagent, I'll do that. But right now that's beyond what I want to accomplish. In future classes, we'll do that. So we know how we can make the aldehyde. What kinds of reagents can we use? PCC, Smyrn, Desmart. We can further oxidize that aldehyde up to a carboxylic acid using all of our strong oxidizers. Things like KMNO4, things like hydrogen peroxide, things like even oxygen gas, potassium dichromate, and chromic acid with sulfuric acid, the so-called Jones reagent. So this is our scheme for oxidizing a primary alcohol all the way up to a carboxylic acid. Well, now what I want to do is talk about the reverse. So what would be the reverse reactions of this? How do I, quote-unquote, reduce from the carboxylic acid back down to the primary alcohol? And we've already seen some of those reactions in terms of converting the OH group to a chloride, and we'll go back over those in subsequent lectures. But I can go all the way down from a carboxylic acid all the way down to a primary alcohol using the strongest reduction reagent with the lithium aluminum hydride, followed by a then H plus H2O step. Okay, so we can reduce this all the way down to the primary alcohol. And the only question is, what would be the mechanism of this reaction? And I think I'm going to go over that mechanism a little bit later because it's in an upcoming reductions of different carboxylic acids. And I think I gave this mechanism in an earlier lecture, but I want to go back through it. But I'm going to hold off on that. So the thing to remember now is if you reduce a carboxylic acid, it goes all the way back down to a primary alcohol. Is there a way to stop at an aldehyde? There will be, but not right this moment. So the last reaction I want to end this lecture with is the idea of doing what's called borane reduction. So borane is, we're going to use the carboxylic acid and we're going to react it with BH3 this is always like BH3THF is what it's called. Now, just to show you what this looks like, remember that borane is BH3. Where have we seen borane before? We've seen it in hydroboration oxidation. Now, what's THF? THF is tetrahydrofuran, which is not aromatic, that's furan. And what happens is that boron, only having 6 electrons, will form a coordinate covalent bond with the THF. Coordinate covalent means that the oxygen donates both of the electrons to form the bond. Okay, so technically the boron in this case would be negative and the oxygen would be positive, but this is called the BH3-THF complex. So in this reaction, we still have borane giving H minuses. And so when you do this reaction, you will reduce the carboxylic acid down to the primary alcohol. But the nice thing about this reaction is it is specific for carboxylic acids. In other words, the BH3-THF will only reduce a carboxylic acid. It will not reduce aldehydes. It will only reduce carboxylic acids. And also this will not reduce ketones. So if you had a ketone or an aldehyde or a carboxylic acid and you reacted it with lithium aluminum hydride, you would form a secondary alcohol or a primary alcohol, or again a primary alcohol in the case of the carboxylic acid. If you take the same ketone, aldehyde, carboxylic acid, react it with BH3, THF, the borane, you're going to get the primary alcohol from the carboxylic acid. You're going to get no reactions from the ketone and from the aldehyde. So this is a selective reagent to only reduce carboxylic acids, and that's what makes it special and useful. Okay. All right, so that's going to be the end of this lecture. We will pick it up with more reactions, some review, and we'll talk more about the reactions of carboxylic acids to make other types of carbonyl compounds, also in mechanisms.